Hello and welcome back, Year 11. This is lesson 4 of the radioactivity booklet. The title, Radioactive Decay, it's lesson 4 and date, please underline all at the top of page 23. Quick look over what it is you need to be learning today. So it's lesson 4, we're doing pages 23 to 31. There's 3 parts of the spec that we're going to be learning. 2 on this table, D and E. Let's have a quick look, see what they are. Right, firstly then, we'll be learning about what's called background radiation and be able to make an allowance for it in measurements of radiation. That there's a random nature of radioactive decay and consequences when undertaking experimental work requiring repeat readings over a period of time. And finally, we'll be learning about the natural and artificial sources of background radiation and discuss the reasons for the variation in radon levels. Obviously pause the video if you want a closer look at those learning objectives on the specification. Now, before we get started, there's 3 main pictures here that are trying to show the same thing, and it's showing that the rate of radiation does not get affected by fire, by chemical reactions, or by temperature. But before we make a few notes on that, let's just do a quick recap on what radioactivity is.
These canisters hold plutonium. If the energy locked in them were released all at once, the result would be an explosion. So every canister is individually marked and accounted for. Under highly controlled conditions, nuclear power stations release the energy slowly to make electricity. The energy and radioactivity come from the plutonium nucleus. The nucleus of every atom is made up from protons and neutrons, about the same number of each. The nuclei of most atoms stay like this forever, but radioactive nuclei are unstable. They're like pieces of popcorn waiting to pop. Once in its life, a radioactive nucleus decays and throws out part of itself as radiation. Some atoms throw out a pair of protons and a pair of neutrons together as a particle. This is alpha radiation. In another nucleus, a neutron might suddenly change into a proton, throwing out an electron at the same time. This is beta radiation. Gamma radiation is an electromagnetic wave with very high energy. It's sometimes given off by a nucleus which has just decayed in another way, as the nucleus struggles to make itself stable. Atoms of the same type always decay in the same way, so it's often possible to work out what type of atom is involved by detecting and measuring radiation. The radiation is a telltale clue to the atom which created it. Alpha, beta, and gamma radiation have different properties. Alpha radiation doesn't travel far in air. A sheet of paper will usually stop the alpha particles completely. Beta radiation is more penetrating. Paper has little effect. But beta particles find it difficult to pass through denser materials like perspex.
Now, you will hear that clicking noise in the background, and that clicking noise is a measurement of how much radiation is being detected. The faster the clicking, the more radiation. In today's lesson, we're going to be learning about background radiation And background radiation is the radiation that is around us all the time. And somewhere like Ponte Ice, you would be having a background radiation count of about 17 counts per minute. So you'll have 17 of those clicks, click, 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 17 times a minute. But it's a random process. It won't be 17 every minute. It could be 19 one minute, 17 another, 16 another, 24 another, 12. You get it. But the average is 17 counts per minute. Background radiation.
Beta radiation is more penetrating. Paper has little effect. But beta particles find it difficult to pass through denser materials like perspex. Gamma radiation is the most penetrating of all. Only very dense materials, like lead, will greatly reduce gamma rays.
So before we do a bit more work on background radiation, just consider the situation here. Those measurements being made would not be affected by these three, by fire, by chemical reaction, by temperature. I made some notes there for you, so you can pause the video and make your own notes on that. So how do we monitor radiation? Well, we use one of these. It's called a Geiger counter, or in full name would be a Geiger Mueller tube, but shortened down to Geiger counter. And you can see what happens here is that we'd have perhaps an alpha particle or a helium nucleus. Alpha particle would go in and it would ionize an atom, and it would cause an electron to get attracted towards this anode. Remember, an anode is positive, and the electron would go through that anode and it would go around the circuit and it would be registered here. So that would change it from 9650 to 9651. This is a photo of the type of Geiger Mueller tube, Geiger counter we have in school, and you can see the units there are counts per second. And as I said a few moments ago, background radiation, if there's no radioactive source present, then 17 counts per minute would be the background radiation for Ponte Ice. Now, different parts of the country would have a different background radiation because of something called radon gas in the atmosphere coming from underneath the ground. But we'll learn more about that later. Now, what I'd like you to do next is to fill in the blanks in the paragraph underneath. And the point being made here is that because of the random nature of radioactive decay, it means that repeat readings need to be taken. I mentioned a few moments ago that the background radiation could be 17 1 minute, it could be 24 another, then 12, then 16, and perhaps 28. Because it's random, what we need to do is take repeat readings, because repeat readings give you reliable results. Alternatively, you can take many readings over a lengthy period of time. Let's say that rather than measuring for 1 minute at a time, you could measure for 10 minutes. So you take a 10-minute reading, and you might get 170 counts being read over 10 minutes. And you just would divide that 170 by 10. 170 divided by 10 will give you 17. So there's two ways then, effectively, of taking more reliable readings. Repeat readings or over a longer period of time. So fill in the gaps there. Repeat readings need to be taken to ensure reliability. Alternatively, many readings need to be taken over a lengthy period of time. It could be 10 minutes, it could be 3 hours, it could be even longer. But you just divide by the time that's been used to make the total measurements. So Geiger counters will pick up radiation from any source. So in order to detect any potential leaks from a nuclear power station, they need to know the level of background radiation. We're going to be finding out now where background radiation comes from. It comes from a range of different sources.
Radiation naturally. This natural radiation due to air, rocks, soil, water, vegetation is called background radiation because it's there in the background. There are these alpha and beta decays occurring. The most common source of background radiation is a gas released from the ground called radon. Because the radiation from radon can be higher than safe levels, people often test for this gas using kits that they place in their basement. But you might be wondering, how do we test for radiation? How do we detect it? Well, radiation can be measured using a Geiger Mueller tube. So here's what that looks like. You've got this tube with a gas inside.
Okay, we've already looked at a Geiger Mueller tube. Just remember then, background radiation, it's all around us. Now you need to take into account what the background radiation is to work out how much radiation is being emitted from a particular source. You have to subtract from any measurement taken. Let's look at an example of that. Right, so to the left are two readings taken using a Geiger counter. The reading units are counts per minute, so you could put CPM there, counts per minute, after each of those. And that's the number of ionization events per minute. We just talked about that, how the Geiger Mueller tube works. The higher reading, 956, was taken at a nuclear power station where there's a suspected leak. The lower reading was taken in a nearby room where there was no leak. So we would, where there's no leak, that's what we would class as our background radiation. And we need to take away that background radiation to get a true measurement of the radiation due to the leak. If you look at question 1 or 2, you should be able to answer that and that now. So pause the video and do so, and then we'll self-assess after. Okay, so what you should have written down for question 1, background radiation level is 27 counts per minute, CPM. What was the radiation level due only to the radiation leak in the storeroom? All you have to do then is take away that background radiation from the measured level, and that will give you a reading of 929 counts per minute. So that is not background radiation, that is the radiation level due only to the radiation leak. Okay. If we now look at sources of background radiation, you've got 8 different sources here, and above each I've written down their percentage contribution to background radiation on average. what I'd like you to do next as the activity is to work out the percentage of background radiation due to the human body. So what I'd like you to answer that obviously here. So this is going to be another self-assessed question. Show your workings please here and pause the video now. Okay, now what you needed to do here was to work out what's the percentage of background radiation due to all the other sources. Add those up and then take it away from 100%, and then that should give you this answer. So I've just summarized that here. So percentage of background radiation generated from humans is 100%, take away percentage of all other sources. Then underneath here, I'm going to add up all those other sources. So they're all adding up to, oh, wrong pen. They're all adding up to 93%, I think. Please check that yourselves. I may have made a mistake. And then you go back to this original equation or formula and percentage of background radiation. So that'll be 100%, take away 93%. Now please take time to present your answers similar to what I've done here. It takes more time, but it shows that you're thinking clearly, and it shows whoever's assessing your work or marking your work that you've understood the question. And even if you make a mistake at say this point here, which is easily done, if you just put down a final answer and get one part wrong, you won't get any marks at all. So again, get in the good habits. Good habits die hard. Question 2. Construct a pie chart to show the sources of background radiation using a protractor. So I've made a quick start on how to present or show the proportion of X-rays. What you would do, look, you would work out the angle of X-rays by dividing the percentage of X-rays, which is 15%. Oh, there it is. You get that 15%. You divide that by 100% and multiply by 360, which is the number of degrees in a full circle. Remember 180, if you do a 180, you go around half a circle, 360 all the way around. And so that's 54%, or 54 degrees, sorry, 54 degrees. And the way I would have to work that out using my protractor, I'd have to, it just so happens that this particular software, OneNote, hasn't got a protractor, so I'm going to have to use this ruler. And if I start from 90 and I take away 54 degrees, I'm going to go to 30, take me to 36 that I've shown there. But using a protractor, you wouldn't have to do what I've just done. You'd have just put the reference 0 degrees at one line, and I'll make a mark at the angle you require. So I'm just going to put that in there now for X-rays. And you can complete that. This isn't going to be a self-assessment, this is going to be a teacher assessment. Right, so you just complete that yourselves. And what you're going to have different lines separating the different sources that are contributing to the background radiation. Please take your time, do a neat job, use a calculator, use protractor, use pencil and a ruler. So that's a teacher assessment. Okay. Mentioned earlier about radon gas. Radon gas comes from rocks underneath the ground. I'm going to pause the video. No, you're going to pause the video, I should say, so that you can read to yourselves this paragraph and find out more about radon gas. So can you do that now, please? Okay, now you've read that, you can see underneath that certain parts of the UK have got much greater levels of radon gas than others. You can see down here in Cornwall, particularly high levels of radon gas. And yes, we live here, look. This is Polydelice just north of Swansea, somewhere around there. There in fact is Loch Estree, so we're just about here. Whereas somewhere in further east, like in Cardiff, you get much higher levels of radon gas, and in some parts of Cardiff, they wouldn't build houses due to particularly high levels. Or if they do build houses in certain areas, they've got to put control measures in place. Now, one way in which radiation can be measured is using sorry, my OneNote was playing up there. I'm just about to say, one way in which radiation dose can be measured is using this unit called a Sievert. Now, it's a measurement of how much radiation we receive, a person receives. And it's a big unit. So we use milli. Remember, milli is 10, it's not someone's name, milli is 10 to the minus 3, which is 1,000th, 0.01. So a millisecond would be 1,000th of a second, and millisievert therefore is a thousandth, bit of a tongue twister, of a sievert. So the average annual dose received from a radon throughout the UK is 1.3 millisievert. But in places like Cornwall, where there's lots of granite which produces radon, can be, what's that, almost 4 or 5 times higher, 6.4 millisievert, yeah, nearly 5 times higher. Radon gas. So if you turn now please on to the next page. What's the problem with radon gas? I'm going to talk about measures that can be put in place, as I mentioned earlier, to reduce the amount of radon gas that can get inside a building. So that's the question here. How can you reduce the buildup of radon gas inside the building? Well, one thing that you can do is make sure there's good ventilation in the house. So that means the amount of air that can circulate, because the radon gas, of course, comes from underneath the ground and can seep through the floor into the ground, into the rooms downstairs, I should say. So your next task is to summarize how could you reduce this buildup of radon gas. We're going to watch a quick video now, and at the end of the video, what I'd like you to do then is just summarize in these lines below on what prevention methods can be used.
Positive pressurization involves the installation of a special fan, either in the loft or on the internal side of an external wall. This draws clean air in from outside and disperses it through the building. The air pressure in the house is raised slightly, which stops radon gas from the soil being sucked in. Another method is the use of a radon sump. A hole is drilled underneath the building and a small void is created. This void becomes the lowest point of pressure, so any gas in the soil is attracted towards it. A vent pipe incorporating a fan is installed from the void and runs to the top of the building, where the gas that has been collected is discharged safely into the atmosphere.
Once you've summarised and made your notes on how to protect against radon gas, turn on to page 28, where we're learning about cosmic rays. Cosmic rays, they come from outside the planet, and you can see these cosmic rays here, look, coming in from outside the planet and zapping the Earth or irradiating the Earth. It's a natural form of radiation, so what I'd like you to do now is just write down another natural radiation here and two artificial ones here. Artificial meaning human-made. If we go back to just above the pie chart, you can pick out a couple of human-made examples of, here we go, of radiation. Nuclear bombs, for example, air travel, X-rays. So you can pick two of those three and then just write them in these boxes here and pick another one for another natural form of radiation. I'll pause the video now so that you can read that. If you pause the video now just to read that paragraph highlighted here. Okay, once you've read that, you look at this discussion point underneath. It's making a point here that you get a bigger dose when you're on an aeroplane. In a 1 hour flight, you'll increase your dose by that much. So do frequent flyers and cabin crew have to worry about the increased background radiation due to cosmic rays? Well, in order to answer that, you need to know what would be a dangerous level and also how much they would receive. Okay, to answer that question, then we need to know what would be a normal level. So if we go back up a few pages, we can see, if I draw a circle around it, it says the average annual dose received from radon throughout the UK is 1.3 millisieverts. 1.3 millisieverts. Let's compare 1.3 to a 1 hour flight, so that's annual UK average. A 1 hour flight we'll write that the other way around so it's easier to follow. 0.005 millisieverts and if we compare the two, we would divide 0.005 into 1.3. So if I just do this calculation, and we can see how many of those 0.05s go into 1.3. In other words, how many hours flying is the equivalent of a year's exposure. and that comes to 260. So you'd have to have 260 hours of flight time to have the equivalent of a year, the average UK annual exposure to radiation. Most people wouldn't be anywhere near that level of time in an aeroplane, apart from, of course, perhaps cabin crew and pilots. So then, therefore, pilots and cabin crew must monitor the amount of time they fly in an aeroplane. Now, there's other ways in which people's exposure to radiation can be monitored, apart from keep a record of flight time. Turning on to page 29. What we're looking at here is a different way of monitoring exposure to radiation sources. So again, what I'd like you to do now is to read these two paragraphs and pause the video and then press play when you've completed reading those two paragraphs. So the way in which this this badge or dosimeter works is that inside it you've got some photographic film, and the more in which the film is exposed to radiation, the darker it will get. So every time some radiation collides with a photographic film, it gets darker and darker. But what we want to know as well is what type of radiation is hitting the film. And the film is split up into three parts, and you can see that here, A, B and C. So the film split up into A, B and C. Before we consider that further, let's just make sure we understand what radiation can get through to A, what can get through to B, and what can get through to C. If we take each of those, A for A here, look, there's nothing in front of the film. So that means that alpha, beta and gamma can all have an impact on the exposure. So you'd expect that to be darker than the other two if alpha was colliding with and irradiating that photographic film. So materials that make up this badge, that's just the film itself. Just the film. Whereas B is the film and lead, and C is film and aluminium. Now, if you look at C, there's aluminium. It's on part C, meaning that beta and gamma could get through, but not alpha, because aluminium would stop any alpha getting through. on part B, section B I should say, it's only gamma that can get through lead. Therefore, let's say you had a film that looked like that. That would tell us that only alpha was affecting the film, because alpha wouldn't get to C, it wouldn't get to B. If we had one that looked like this, where it's dark on A and B, then it would tell us that beta is getting through. If we had a film like this, where we had, right, C, A and B again, and this would suggest that you're getting alpha and beta hit in there, and only beta hit in there. So that's a way to, and anyone that's perhaps works in a nuclear power station would need to, or in a hospital with X-ray machines, would wear those badges to keep a record of how much radiation they've been exposed to. Now the last activity, it goes over page 30 and 31, is a comprehension activity, and you need to give your written answer on study zone. So you read these 2 pages, 30 and 31, and there's a written 6-mark style question, as you would have in an exam, on the study zone for you to complete when you've finished this lesson. So that's lesson 4. So make sure then please you've completed your booklet up to page 31. You should have done the starter retrieval assessment at the start of this lesson, and now please go on and complete the written assessment. See you next time. Bye.